Welcome to week 7 of our class, and you must be excited because we're kind of finished with the circuits portion of our classes so far, and that includes EE 188 and then the first half of EE 280. So we covered almost most of that first textbook, Electric Circuits by Nielsen and Riedel. So we have put all that behind us, or we are putting it behind us, and we begin almost a new kind of material for the rest of this course. And of course, you will also take another course to continue what we begin here on semiconductors and electronic devices. So the textbook that I'm going to use for the remaining 6 weeks of this course, and also what you'll use in E380, is a very famous and important textbook for electrical engineers. It's called Microelectronics by Cedra and Smith, and ideally I want you to have the 6th or 7th edition. They are telling me that the Chinese edition is only a translation of the 5th edition. So if that's all you can get, that's okay also. But it would be nice to have the newer edition, 6th and 7th. I think they're also on to an 8th edition. So one of the things about the textbook itself I noticed is that the Chinese version, the 5th edition translation, actually does not have this chapter that we are going to cover. This chapter, called Semiconductors, is only been brought in the newer editions. Unfortunately, you may not find it in the Chinese edition. So yeah, I guess either you have to rely only on what I'm giving you in this PowerPoint and these lectures, or I'm sure there's plenty of other good books in the Chinese language if that's what you need to help you on semiconductors, or also called semiconductor physics. So please look around and see if you can find more material, because more material always helps to make things even clearer than just following one textbook or one lecture, right? Okay, so with all that, let's try and get started. I will, hold on one sec. I want to put in slide numbers so that I have some reference on each slide. Okay, so let me skip past slide 1, which was just the title, to actually looking at the all the specific topics in this chapter in the textbook and what I intend to cover. So there's an introduction plus 6 sections or 6 topics, and my goal is to do 0, 1, 2, 3 on day 1 and 4, 5, 6 on day 2. So we will look at semiconductors and their basic properties, and then section 3 is called current flow. So we'll address those, do some problems, and then move on to the next 3 sections. Okay, so that was slide 2, and I will move to slide 3 in a minute. So one thing I did want to emphasize is that we will be looking at semiconductor behavior or semiconductor physics in a very elementary way. I am certainly not going into a lot of detail. I don't know if you folks have a course called engineering physics or advanced physics where you do study semiconductor physics. If you do, this will just be revision. If you don't, then a lot of this will look like it's all new. I mean, it still is basic physics and chemistry, which, we all learned in high school. So a lot of that is really all you need. But if you did get a chance to do a little more, just focusing on material science or semiconductor materials in particular, that would have been great. But if not, I will cover it in a very basic way. You know, it's it's maybe not even absolutely necessary. That's why this material was not in the textbook up to the 5th edition. They only brought it in the 6th and later. So you can think, oh, this is not really needed to understand electronics. Maybe that's true, but it certainly helps if you know this. It certainly, it can better help you understand electronic device actions and circuit behavior if you even understood a little bit of the physics. So having said all that, I will try and cover it to some level, enough for us to understand, to do some problems, and then move on to other exciting things like, diodes and bijunction transistors and CMOS field effect transistors and so on, and of course integrated circuits and all that. But I won't go into too much detail, and those who like to get more detail, I'm sure there's many other great textbooks and material available online and in the Chinese language that you can definitely refer to if you feel the need for all of it. I'll try and cover it to the extent that is required for us to get through this course, okay, with a good foundation. I also assume that most of you will have some understanding of basic atomic structure, electrons, protons, atomic number, valence electrons, etc. Energy bands maybe a little bit also. So if you have some exposure to all that, then you can get to understand this immediately, the following material. But if you need to revise basic atomic physics, I suggest you stop, go back, look at some of that, and then come back. Okay? All right. So let's move on, and I am on slide 3. What am I showing you here? According to the band theory of the atomic structure, there is for a lot of for all elements in the periodic table, and I'm sure you know what the periodic table is. It's the list of all the elements on Earth. I think it's up to 115, 116 or whatever now. And for each of the elements, there is an atomic structure. There's electrons, there's a nucleus, and then there's neutrons and protons within the nucleus, and then electrons outside it. And so these electrons, they live in different energy bands, and the outermost band where all the electrons reside is called the valence band. Now the valence band is separated from another band called the conduction band. And what has been discovered is that when current starts to flow, or for current to start to flow, to exist in a metal such as copper or any other, all the available electrons actually first move into the conduction band. That's where they are, and then they start jumping from one atom to another along the wire, the copper wire or aluminum wire, and thus cause electricity. But if you look at the atomic structure, all of these electrons are in what's called the conduction band. That means they have a certain amount of energy that puts them in the conduction band. So the valence band is not the conduction band. They are two separate items, obviously. So certain electrons reside, there's always electrons in the valence band. That's the outermost band of energy that the electrons possess. And some electrons from the valence band can make it to the conduction band. Not all the electrons can do that, but some can. And only in real conductors like copper, it's very easy for these electrons in the valence band to go to the conduction band and then become part of the current flowing into the wire. On the other extreme is the insulators, so plastic, for example, or rubber. These never conduct electricity, right? So the electrons in the atoms that form plastic, they or other insulation material, right? We know plenty of insulators. So other insulation material, their electrons in the valence band, they are never able to go to the conduction band. That's why they're called insulators. They cannot ever conduct electricity. So semiconductors lie in the middle. They are not completely insulators, they are not completely conductors. They always have a lot of electrons in the valence band, and it's possible to push those electrons into the conduction band somewhat easily. It doesn't happen too much, but there's ways to make it happen so that at least the possibility exists for current to start to flow in a semiconductor material also. Okay, so I wanted to give that very brief introduction to semiconductors before we start proceeding into our textbook and our material. Okay, so if you need more of this, you should look at some new books on physics and semiconductor physics, but this is the most basic introduction. So the two bands are valence band, as I show here, is the energy range. The orange band is the energy range within which all the outer valence electrons of an atom lie. And the conduction band holds all the free electrons responsible for electrical conduction. And you see that there's a gap between the two. The gap is very big in an insulator. It's greater than what's called, the gap is measured in electron volts, and it's 9 electron volts here. It's only 1 electron volt for semiconductors, and for a conductor it's all mixed up, meaning there's almost no separation between the valence and the conduction band. Okay, so the reason we like semiconductors is because of the fact that they are not conductors fully. They are not full conductors and they are not full insulators, but the fact that we can control how much electricity they will allow to flow at any given time, we are able to control it by artificial means, and that is what gives semiconductors that great power that we use to benefit us in the electronics industry. Okay, all right, so one more slide, one or two, and then we should get into the real material in the chapter. Here is a section of the periodic table. You know what the periodic table is? All of the metals and the elements are listed, and here what you see is they're separated by these numbers 3, 4 and 5, and these are the number of electrons in the valence band or valence electrons. So this shows you some elements which have 3 valence electrons, 4 or 5, and you'll notice silicon is right in the middle. It has 4 valence electrons and it has a certain behavior. At 0 degrees K, that means 0 degrees absolute, which is actually minus 273 degrees centigrade, silicon just behaves like an insulator. But at higher temperatures, that means well above absolute 0. So even at room temperature, which is well above absolute 0, right? Room temperature is about 300 degrees K. The free electrons are released from the valence band and move to the conduction band, some free electrons, not a whole lot but a few. So that's why I added some. Now the same effect of having electrons available can also be achieved by something else called doping. So when you take silicon material or a bar of silicon and add certain elements, these are called impurity elements, not that there's anything wrong with them, not that they are not pure, but they just call that. But they have a certain type of atomic structure which helps to also make more electrons available in silicon for conducting electricity. Okay, so that process is called doping. So that was slide 4, by the way, and I will move to slide 5, where I am introducing some material a bit too early, so don't get too frightened if you don't understand. But what I wanted to show you is that there's a top box called intrinsic semiconductor and a bottom box called extrinsic semiconductor. And you'll see what the difference is. We're going to spend a lot of time studying these, but there's two ways that silicon, which is basically a semiconductor, can be an intrinsic semiconductor or can be an extrinsic semiconductor. That means intrinsic meaning natural, and intrinsic also makes some electrons available for current to flow. Extrinsic is another process using doping, as I just talked about, also to make some more electrons available for current to flow. Okay, so both these types we'll study. By the end of this chapter you'll understand pretty well, I hope, what the two types are. Okay, but I just wanted to show you a quick introduction. Okay, one other important thing that I wanted to mention right in the beginning. Again, this table is actually, it's 3 slides, slide 6, 7 and 8. It's one table in our textbook, and I just chopped it into 3 pieces to show them here. But the point I wanted to make here is this chapter is likely to be a bit complex. So far, I think in almost no other chapter have we studied so many equations all at once, and they all seem like a big mess with lots of constants and lots of equations, derivatives, Greek letters like you can see rho and micro and what else, epsilon, and all this stuff. So it seems like it's a little bit too much, but we will work through it one step at a time. I just wanted to show you that they're all easily available in one table to use, and the mathematics that we will do here, it's actually quite simple. It's basically algebra. We don't really use almost no calculus here, a little bit, but basically it's manipulating numbers algebraically. One of the problems again is, look at the kind of numbers we have. These are either very, very large or very, very small. So you have 10 to the power 15, because there's so many electrons in an atom, right? So that's why these kind of huge numbers come about. Then we have very low numbers like 10 to the power minus 5 and so on, because we are looking at the most basic units of charge, right? So all this makes these numbers look big and look small, but that is one of the peculiarities of this topic, particularly semiconductor physics. It's not so bad once we finish this chapter and we start doing actual circuits and devices. But even here, I will say that in electronic circuits, you can't quite go away from this kind of stuff. So you better start to get a little bit of practice and comfort manipulating these kind of numbers. So anyway, I just brought this table together. This was actually at the end of our chapter 3 in the textbook, but I brought it forward just so I could introduce you to it early and tell you that you can always keep looking at the summary of the formulas so that you will be able to solve problems quickly. Okay, so let's finally begin the actual chapter and look at section 3.1. So many of these drawings are taken from our textbook. A few I may have taken from somewhere else, but I hope if you need more. I know this may not be in the Chinese language edition, but if I will, maybe you can find a PDF of the English language and read through all of this also, because obviously I can't cover too much. You might have to read the chapter a couple of times yourself. There's a lot more in the textbook than I can ever complete. I'll try to give you the summary, but again, see if you can somehow get at least a PDF version of this chapter in English also for your reference. Okay, so on the left side is the structure of how silicon atoms individual atoms are held together to make silicon, the silicon molecule, right? A molecule has many atoms, and then molecules together make the actual material, the metal. So as you may remember from physics from high school, atoms are held together by something called bonds, and there's a covalent bond between two silicon atoms that keep everything together. So a silicon atom, let's say this one in the middle, has 4 electrons, and so it makes connections to 4 other atoms in the neighborhood. Okay, so this atom is connected to 1, 2, 3, 4, and that connection to the neighboring atom is the bond. Okay, and there are valence electrons, so there's 4 protons within the nucleus, and there's 4 electrons outside, right? These 4 electrons outside the atom is called the valence electrons. So these 4 valence electrons are held to each other in this molecular structure, and the bonds are called covalent bonds. Now let's look at the right. So what has happened here is, now this condition exists when the temperature is absolute 0. That means it's freezing, it's very low temperature. But at room temperature, some thermal energy is available to the atom. And so this thermal energy automatically creates free electrons, and these free electrons are shown here. So for example, again in this center atom, silicon atom, one of the 4 electrons has become loose. It's not held in a bond, and so this dashed bond is called a broken bond. So this broken bond has created a loose electron, a free electron, and in its place there is what's called a hole. A hole is the absence of an electron. Okay, and both holes and electrons are very important to understand electronic circuit behavior and actually device behavior. And so I want you to become comfortable with the idea of a hole. A hole is where there is no electron, or the absence of an electron is called a hole. And you can see why even understanding holes is important in a minute. But for now, I just want you to understand that even at room temperature, because of the natural hotness of the room, of room temperature provides free electrons are available to move around, and that's why these electrons are called intrinsic. Intrinsic is something that is natural. Nothing external needs to happen other than, of course, the temperature, the room temperature, but nothing else. And that is called intrinsic behavior or intrinsically available free electrons. Okay. So I'm going to move to the next slide. Now we are on slide 10. And this material is from a different textbook. But I feel this will also explain to you pretty much, it's really trying to cover the same thing that we just covered in the previous slide, but this gives a little more of a certain process. It better explains intrinsic semiconductors. So what am I showing here in this drawing? So the top portion where I say free electron release due to thermal energy, on the left you see one silicon atom, and it is the 4 electrons are shown in this way by this textbook compared to how it was the previous way. And you see the covalent bond and how the atoms, individual atoms, are all together to form a silicon molecule. And here again you see that one electron has become free from this particular silicon atom. So this atom had 4, but one of them got free, and so it's floating around. It's a free electron or a loose electron. Okay. Now here's something to the right here, top right. The minimum energy required to dislodge an electron from a covalent bond is called Eg, and you'll see this Eg quite often in electronics. So this band gap energy for silicon is about slightly more than 10% more than 1 electron volt. And I think I showed you this when I showed you my very first slide where we talked about the valence band and the conduction band. But when an electron has acquired an energy slightly greater than Eg, it becomes loose. So if more electrons get this energy, then they start becoming more and more freer and loose electrons available. Okay. So that's the minimum energy required to dislodge an electron from a covalent bond, to pull it free from the bond. Okay. Now let's look at the bottom portion a little bit. What you see here is what's called left to right movement of the electron. So let's say an electron became loose here, and in place of the electron we have what's called a hole, right? What's left behind is a hole. Now the electron got acquired by the free electron got acquired by another atom, right? The free electron is not just sitting there. Maybe another electron already had a hole because its electron got free. And then this electron from atom number 1 jumped into that hole because the hole is natural attraction, holds a natural attraction to a free electron, right? It's a lack of charge. So an electron jumps into this atom, and so you see that the first electron, a first atom, now it has all of its electrons back, but the second atom now has a hole because it has a free electron. Similarly, at t equals time 3, this was t equals time 2, now we are looking at t equals time 3, this electron, this atom, it got all of its necessary electrons, all 4, but the one next to it now has a loose electron and hence a hole. So you can see that this process continues, and it's almost like electrons are moving from left to right, which they are because they are looking for holes in the neighborhood to jump into, and then once that happens, maybe another free electron gets out and the process keeps continuing. And this can happen a lot at room temperature in silicon, in a semiconductor material. Okay, so that's what this is supposed to show you, that a natural movement of current of electrons actually happens. Okay, all right, so I'm going to move to slide 11, and we still are in intrinsic semiconductors. We are only still talking about all that happens at room temperature with nothing external being brought in. Okay, and here also there's a bunch of formulas and new items to understand. So let's see if I can walk you through these quickly. So for silicon, there's something called N equals P equals Ni. N is called electron density and P equals hole density. And what does this mean? It's the number of free electrons per unit volume in intrinsic silicon. That means, okay, so we know there's a big bar of silicon, but how many electrons are available? How many free electrons are available at any given time? And that number is called Ni, and it's also equal to N or P. Sometimes they drop the I, but you'll generally know it if they drop it, as to it's not necessary. But generally speaking, the number of free electrons equal the number of free holes. P is the hole, right? We represent N with electron is represented by an N, and hole is represented by a P, and so number of free electrons per unit is Ni, also sometimes called N or P, per unit volume, right? So unit volume meaning, let's say 1 cubic centimeter of silicon. In 1 cubic centimeter, 1 centimeter by 1 centimeter by 1 centimeter block of silicon, how many electrons are there, right? That is one way to find out or to say how many electrons exist. So that is the terminology, and you should become comfortable with this. Then there's a formula, and again all of these formulas come from physics. I may or may not have time to look at each one in detail, but I'm giving you what is necessary so that we can solve problems and keep moving. T is generally shown to be in degrees Kelvin, absolute scale of temperature, so you want to become comfortable with that. So let's look at one equation here for Ni. In intrinsic electrons, the electron density is given by this formula. B is called the Boltzmann constant. This is the value. T is the absolute temperature raised to 3 by 2 exponent minus Eg. We just saw Eg in the previous slide, divided by 2 kT. K also has a value here, okay, 8.62. So there's all of these values and these large numbers and small numbers, and we just have to learn how to work with these. If you're really interested in a lot of physics, please go ahead and look at the textbooks that give you all the derivation. But for our purposes, we just need to know the meaning of each of these and how to use them. Okay. So Ni, actually, if you put all these values in, it looks like this, the equation. And if you plug in T and you plug in a value of Eg, you actually get this. At room temperature, Ni is approximately equal to 1.5 into 10 to the power 10 numbers of free electrons per centimeter cube of silicon, of pure silicon. Now you may think, whoa, this is a big number, right? But actually this is very, very small compared to the total number of electrons in 1 cubic centimeter of silicon. This is very small. This only says it's 1 free electron for every 5 into 10 to the power 12 atoms per centimeter cube. So the number of free electrons, because of natural temperature, the presence of room temperature, is very, very small, but still much bigger than 0, of course. Okay. All right, so that was slide 11 and a quick introduction to intrinsic semiconductors and these factors, Ni, N, P, density, and all the other stuff. Okay, now we move to doped semiconductors, and this is topic number 3.2 in the chapter. So what are we doing with when we say we are doping? When we say doping, we are bringing in one of two types of material into the atomic structure of a molecule of silicon. So, if you bring in something like phosphorus, which is another element, and it happens to have 5 electrons, 5 valence electrons, if you bring that in and it gets embedded into the atomic structure, into the molecule, then such a doping is called a donor doping. That means it's donating an electron because it has 5. And there's another type of doping called acceptor doping. Here, an atom, another material, it's actually boron. So boron, which only has 3 electrons in its outer shell, in its valence band, if that comes here, then it grabs an electron, right, from silicon, because it only has 3, and to form a covalent bond you need 4, so it takes an atom, an electron. Okay, so you see there are two types of doping. One is called donor doping and another is called acceptor doping. And a donor doping, it creates a free electron because it already had 5, it sits here with 4, and so 1 is loose. So a free electron has come into this structure, into the molecule, because we brought in the donor, the doping donor, phosphorus. And even though we call these impurities, because you have pure silicon and then you have impure, impure doesn't mean anything wrong, it just means a donor came in and gave some additional electrons or took away some electrons and made it impure. So on the right side, the electron is accepted by the atom, by the donor, the acceptor atom. So the doping element is boron here, which is an acceptor. So the doping element takes an electron from a neighboring silicon atom and creates a hole. So you can read here, electron accepted from this atom, thus creating a hole. So a hole is created here, here a free electron is created. So make sure you understand how these two types of dopings, the donor doping, and acceptor doping, how these work and why they are so important to understand electronic material behavior. Okay? All right. So I'm going to have to hurry along. We are running out of time as always. I'm on slide 13. And here are a few more parameters or factors I'm introducing to get you comfortable with doping and what happens to silicon after it has been doped. So when you dope with donor atoms, means we now get what is called N-type silicon, because there's a lot more N or electrons, there's extra electrons On this side, when we dope with acceptor, we get what's called p-type silicon, because there's more positive charges, which are also holes. Those are floating around, right? That's why it's called p-type. So p-type has a lack of electrons compared to intrinsic silicon, and n-type has an extra number of surplus of electrons compared to intrinsic. So here we are introducing some new terms. Nd, which is the number of donor atoms per cubic centimeter per unit volume. Na is acceptor atoms per cubic centimeter, right? So how many new donor atoms were introduced into the silicon, or how many new acceptor atoms were introduced into the silicon? That's what this Nd and Na stands for. After these atoms have been introduced, now obviously the density of electrons and the density of holes, the free electrons. When we say electron, remember, or holes, we are generally referring to free, those that are able to move. So the number of free electrons available now in the doped silicon is different. That's the whole point of doping, right? So what is that value? It's shown as Nn in n-type, and there's also some holes. There'll always be some holes also lying around. You can never have only one type, right? Because this is a dynamic process. Holes and electrons keep coming together and keep disappearing. So the number of holes per cubic centimeter in n-type doped material is shown with like this, Nn and Pn, and similarly you have Np and Pp, okay? And here's an important formula. Now obviously Nd is much higher than N intrinsic, that's why we are bringing it to dope. And then Nn and Nd ends up being the same. So the new density of free electrons roughly ends up being equal to the density of the donor atoms coming in, or the acceptor atoms in this case. So look at these formulas, become a little bit familiar. Also there's another relationship, the product of Pn and Nn equals Ni square, and Pn equals Ni square by Nd. In this case we show Np equals Ni square by Na, okay. In n-type, electrons are called majority carriers and holes are called minority carriers. In p-type, holes are majority carriers and electrons are minority carriers. So please pay attention, try to understand this. This is pretty elementary, it's just defining many things, but you will need to become familiar and comfortable with all this. Okay, so next slide, 14, it's a problem, we'll come back to this, but I have to cover just a little more theory and then we'll stop and get to problems in my next recording. So what is item or section 3.3 in this chapter? In section 3.3 we finally start to look at the current flow in semiconductor material, okay. So obviously now we are talking about doped material. So we have a bar of free silicon and the P is the hole concentration and N is the electron concentration, okay. Given this, you can have two types of currents, a drift current and a diffusion current through the silicon material, through the bar of silicon. Now if this is just doped one type, only P or only N, it's easy, but sometimes you can have both and then it becomes a little complex. But in any case, you'll have both drift current and diffusion current, and it's important to understand the difference. Drift current is when you apply an external source. So if you have a bar of silicon, you kind of doped it also, and you applied a voltage, immediately you'll see this kind of movement of electrons. So electrons, conventional current we always say goes from positive to negative, but we know electrons is opposite, meaning electrons flow from negative to positive. And because of that, we say holes, which is always opposite, they flow from this direction to this direction. Okay. So this is from the textbook. This is a nice graphic. Here's another graphic to talk about diffusion current. So there's no external voltage in diffusion, but let's say we were somehow able to keep adding a lot of carriers, meaning we were able to continuously add holes or electrons, kind of we are doping. How this happens, don't worry about it, but assuming we can, and that we are able to maintain this concentration, this profile, right? This is like a graph. So here, when x is 0, assuming this is x in this direction, so when x is 0, you have a very high concentration of this doped material, either electrons or holes, and then it gradually falls like this. In fact, you can see the holes are being shown in that, moving in that direction. So if you can maintain a concentration like this in the material, then also you have a current. And this is called a diffusion current. And it's very important to understand both types and realize that both these exist in any diode or transistor circuit or IC or op amp that you actually work with on a daily basis. Okay? Alright, so I'm going to move on to slide 17. We have to cover a little bit of the theory on both of these types of currents. So here's a little more, looking only at drift current, and then I look at diffusion current separately. So here are a number of new factors that we are introducing. There's something called J, which is the current density. Current per square centimeter is current density in this bar, and that's shown by J. Now if you multiply J by area, surface area of this, you get current in amps. Okay, so J is current density, amps per centimeter square. V can be Vp or Vn, but it's velocity. It's electron and hole velocity. There's a factor called mu with the micro symbol. That's electron and hole mobility. It's a constant. D is another constant called diffusion constant, diffusivity. Actually, we don't use D here. Maybe I can take it out. It comes only into diffusion here. Q is here. Q is the charge of an electron. You probably know what that is by now. You should. The basic charge. How much charge in coulombs does an electron have? It's about something to the power minus 19. So that is also used in these formulas. E is the electric field, which basically means if you apply 1 volt across 10 centimeters, then the field is 1 volt per centimeter. So the volts divided by length gives you electric field as a simple formula, and then there's something called resistivity or rho. So all these are used in calculating J, drift current density, which is the sum of two sums, hole density and electron density, and each of these can be shown to be this and this. Remember, E is the electric field strength. And then resistivity also has its own formula, and you can write J in terms of resistivity, or you can just write J directly by E multiplied by this. Oh, actually it's here. This is also J. And you see the two velocities. The velocity is directly proportional to the applied field, but there is a constant of multiplication called mu p and mu n with a minus sign. So try to become familiar with these because these are also important ideas. Okay. All right, there's a couple of examples, but before we do examples, I have to finish current flow, so bear with me for 2 more minutes and I'll introduce you to diffusion current. Just like we saw drift current, we now have diffusion current. And what is the magnitude of this diffusion current? You see it to the right, there's a formula that says J total. That is, the total current density will be again the sum of two factors, one because of the electrons and one because of the holes. Sometimes if it is an n-type semiconductor, then this whole thing can be neglected, but if you have both types of doping, N and P, then you should really use both, and we'll see more problems in a bit. But here are some important factors we again will look at. Some of these may be new. Now we know J, we already saw, it's current density, amps per centimeter square. Mobility, we were already introduced. We have a new factor called D, which is diffusivity constant, and that's used in these formulas, and that's related to each other and to something called Vt. This is another big important relationship. In fact, this relationship is called the Einstein relationship. And Vt is something called thermal voltage, and it has a certain value in millivolts at room temperature. So there's all of these new items that we came in from physics. Try to become comfortable. I'll show you how to use these in formulas as we do some problems. And of course there's a Q here. So basically what happens is, because you're continuously pumping in some new electrons or some new holes, you're forcing some current through this bar, right? It's similar to having an external voltage source, but these are considered two different types of currents. One is called drift and one is called diffusion, and you should be comfortable that understanding that they are two separate ones and that they have two separate formulas that help us figure out the actual current densities and the currents using factors such as how heavily is it been doped, how big of a silicon bar is it, what is the volume, what is this profile, right? See, I should mention this. There is a derivative here. The rate of change of this density of N and P. N and P are, remember, N and P are the actual hole concentration, right, in the silicon. Sorry, I skipped. There at 21, slide 21. P is the hole concentration, N is the electron concentration. So depending on how that concentration varies in this bar, because we are pushing in new electrons or holes in here, that derivative is taken into the equation. Okay? So those are the two forms of current. So we were introduced to these two forms of current, diffusion and drift. We also saw earlier what doping means, what is the difference between an intrinsic semiconductor and the density of electrons and holes in an intrinsic semiconductor versus what is the change once we start doping, either with donor type, N-type material, or with acceptor or P-type material. So depending on all this, obviously your currents will have different values because of all these densities are different, and these electron and hole mobilities also determine how much current flows. Okay, all right, I went over about 5 to 6 minutes, so I apologize, but I'll try to maybe reduce the problem session just a little bit. All right, I'll stop now and start with the problem solving recording next.